Hello, everyone, and welcome to MakeLearn 360. All right, so in this video, I want to solve a problem with you to illustrate the concept of um, stress in a boat connection. All right, so in this problem, we have two steel plates, and these two steel plates are to be held together by means of 16 diameter high strength steel bolts fitting snugly inside cylindrical brass spaces. So, if you look at it carefully, what we have here as the hexagonal sort of structure here is actually the bolt, right? And then within this bolt, there is this sort of spaces, all right? There is this spaces right here. So we are saying that knowing the average, knowing that the average normal stress must not exceed 200 megapascal in the boat, right? So in the boat, the allowable average normal stress is 200 megapascal, and then in the spaces is 130 megapascal. So now we are to determine the outer diameter of the spaces that yields the most economical and safe design. All right. So now think about it this way. Sorry. So you have this boat right here. Now, looking at the configuration, this these are steel plates. And then what happens is that as this bolt is connected to this steel plate, there is going to be this sort of tension force, all right? However, there are some spaces which is between these two steel plates. So whilst these bolts undergo tension, um, the spaces undergo compression, all right? So basically that's what is happening here. Now, for the purpose of equilibrium, we can say that so basically in terms of the average stress is going to be the load from the boat divided by the area of the boat, and then the stress from the spacer is the load from the spacer or the spaces, there are two, divided by the area of the spaces. All right, now interestingly, one thing that we can say is that the boat, so in terms of stress, so we can also write the stress in terms of load divided by area, which is pi multiplied by dB. So dB, where dB is the diameter of the boat squared, divided by 4. So maybe we can bring the 4 here. And then similarly for the spaces, now interestingly, you can clearly see that the actual diameter of the spaces is sort of calculated from the difference between the spaces and then the boat. Okay, so then what happens is that, think about it this way. You've got a boat. Okay, let me do it this way. So your boat connection looks like this, and then there is this sort of spacer, all right? And then what happens is that this spacer is actually, so this, what you see here is actually the side view, okay? But then if the diameter of the bolt is this, sorry, if the diameter of the spacer is this, then this will be the average diameter of the bolt. So in fact, the actual diameter for the spacer will be the shaded area here. Therefore, with respect to the spacer, the load, the area is going to be pi, this time around is going to be the outer, which is ds, minus, okay, so let me do it this way. So 4 ps pi into dx squared minus db squared. That's all. All right. So technically, we know from statics that if this system is to be in equilibrium, then we can say that PS must be equal to PB, and in fact that is the statistical analysis of it, to say that the average load by the bolt is taken by the spaces. If that is true, then making let's make PB the subject here. So PB is going to be sigma b pi db squared, then I divide this by 4. Again, if I make PS the subject here, it's going to be what? Sigma s pi dx squared minus db squared divided by 4. So we are saying that for static equilibrium, this must be the same. So static equilibrium. All right. So then if I equate this and this, pi will cancel pi. So db squared on 4, sigma s pi ds squared minus db squared divided by 4. Pi into pi, 4 into 4. So essentially, we have sigma b multiplied by db squared should be equal to what? Sigma s and then ds squared minus db squared, right? And from here, what can we say? So look at this. The steel bolt is having a diameter of 16 mm, right? So then the diameter of the spacer is what we are interested in. So then if we make ds the subject, so let's make ds the subject. So then we can say that sigma b db squared plus no, this one is also supposed to be sigma s db squared. All right. So then it's going to be we want to make ds the subject. So sigma b db squared plus sigma s db squared. All right. So sigma b db squared plus sigma s db squared. All right. So ds squared will be sigma b. Okay, let me factorize this out. dB squared sigma b plus sigma s divided by sigma s. So if we do this, that is the expression to find the diameter of the spacer. So essentially, we are going to get the diameter of the bolt squared, which is 16 millimeters, and then we add the stress. So let's add the stress, 130 plus 200. So 200 plus 130 divided by sigma s, which is the 130. If we do this, dx squared is going to be what? Let's pick our calculators. So it's going to be 16 squared multiplied by 200 plus 130. And I divide this by 130. And what is it? So 649.846. 649.846. Now, if I take the square root, what is it then? So square root of the answer. So 25.49 is the diameter required for the spacer. All right. So this problem has been solved. Thank you for watching. But in practice, 25.49 is almost the same as 25.50. All right. So thank you for watching.